We're just gonna give it about 30 seconds here or so until it turns 1 o'clock, and then we'll start. Sweet, I got 1 o'clock, so let's do it. Welcome to another edition of TecTube Live. I'm Ryan Holger. This is Dave Herman.
Welcome.
Dave's very excited to hear him.
Very
Welcome.
excited.
Which is funny because this whole thing is his idea. He's like, we should have something every month where people can kind of get a little topic and ask a bunch of questions. So we encourage you to ask questions on the topic that we're going to show you, or even later on other topics. If you want to go on a side tangent, we'll try to answer some of that stuff. There is a question box on Zoom here that you can type stuff in. If you're watching this on YouTube, then in the future, you should watch it on Zoom so you can actually type the questions in and we can see them and so forth. But if you're typing questions in on Zoom, we'll answer those as we go. So for this month, normally what we try to do is pick topics that people ask a lot of questions on. So Dave pulled some of the guys in his tech support group. And one of the things that seems to come up a lot lately and basically forever is things like static pressure and airflow. So we're going to focus on that today. But you're welcome to ask other questions if there's something else you've been thinking about, AC-wise or new refrigerants, or thermostat wiring, or whatever weird thing you can think of, feel free to ask that. So we want to show you a few different things here. So static pressure is misunderstood and miscommunicated. People think there's like one number, but there's lots of different static pressure numbers in every discussion. And for right now, we're going to stick on residential furnace ducted systems. That's kind of our focus. But just saying that the static pressure is not enough. It's where are you measuring it? What are you measuring it across? What's involved in the discussion. So we'll try to hit some of those pieces. And then the pressures that you're seeing directly affect the airflow that can be moved in the duct system. And if you don't move enough airflow, then other problems could happen, like high limit trips on heat exchangers, refrigeration system issues, etc. So one of the things that Dave brought up and wanted to show you guys to get us going is what we call product data. So for all of our Bryant and Carrier equipment and other brands, they have all kinds of documents, as you're probably well aware, one of which is called the product data. There's other manuals too, like the installation manual and service and so forth. The product data is good for both pre-sale and post-sale information. And static pressure is represented in multiple places on these documents. I'll try to zoom up as much as I can and not lose everything. So if we look at a particular system here, this is a furnace. Maybe for argument's sake, we'll look at 60,000 BTU, 17-inch wide. I don't know, I always just happen to pick that because, well, that's what we have here in the lab with us all the time. And I'm showing you screens that you're not seeing, which doesn't help you. Show our screen. There you go. So now you can see what we see. We're looking at this particular furnace. It has general specifications on it and efficiency and all that great stuff. And then as you move over here to the right, we have CFM for high and low heating. We have static pressure for heating. Let me move that out of the way. For high heating. And then we have the static pressure at 0.5 inches and the CFM associated with that for cooling. This does not mean the static pressure you're going to see on your project. This is just one snapshot of what could happen. And this is the point at which this piece of equipment is tested. So for heating, they're testing it with 0.12 external static. And for cooling, they're testing it nowadays at 0.5 external static. It used to be 0.1 up until like 2 years ago. Now it's tested at 0.5, which is why all the SEER ratings and everything had changed. We'll show you some tables here in a little bit that show you some other airflows and statics. You can see what happens. But we say this ESP, external static pressure, we wanted to find what that in fact means. So if we look at a pretty basic system here, this is a upflow furnace. So return on the right, going through the filter, through the fan, through the heat exchanger, through an evaporator coil, and into the supply plenum and out through the ductwork. That's our complete, airflow path of a system. External static pressure means external to the specific piece of equipment in question. In our discussion right now, that would be a furnace. So this is our furnace right here. Everything that's not part of that furnace is external. So the coil, external, somebody else's problem. Ductwork, somebody else's problem. Filter, somebody else's problem. In contrast, if you had what Carrier and Bryant call a fan coil, or what most people call an air handler, the filter is physically inside the cabinet. So in that case, the fan system, the internal pieces of the cabinet, and the filter are all internal, and external would mean just the ductwork on that kind of project, because your coil and your filter are inside the box. But furnaces is what most of you guys do, so we'll stick with that example. So obviously you can't really affect what's inside the furnace. You're not going to swap the heat exchanger out to a less restrictive heat exchanger, but you have a lot of control over coils, filters, and especially ductwork on the field side. So those are things that you can determine and measure. So the total external static pressure on a furnace system would be, if you were to take your probe and you were putting it, say, right here at the end of the heat exchanger, or right here, if you want to say that, like at the inlet of the evaporator coil, that pressure that you'd be measuring there would be the supply pressure of the system. Then if likewise you came down and put a probe somewhere over here, see if there's like a way to put like a little highlighter. I feel like there should be a highlighter. Is there no highlighter?
Doesn't sound like you're very well prepared.
I'm not very well prepared. I feel like there should be a highlighter somewhere on here. I just don't know how to use it. We'll do this John Madden thing. It's going to be so cool. So right here, if we measure down here where this blue circle is, that would be on the return side. So this static pressure would be on the return side. This static pressure would be on the supply side. And you would add those two numbers together to get your total external static pressure. However, what a lot of people do is they just stick a probe in the duct right here, and they tell us that's their pressure. Great, that is a pressure. You've measured a pressure, but that is not your total external static pressure, which all the catalog data is based on. So you're telling us on the phone that you have 0.6 pressure. You don't even know what it is, just the pressure I measured, 0.6. And then we needed the return side, add those two together, and that is what's going to start matching up with the catalog. So we needed the whole piece of that puzzle, and most people are only looking at part of that piece. And I got these lines on here. That's unfortunate. How do we get those lines to go away on the wrong screen? Very odd. All right, when in doubt, just start over, right? So that external static pressure on here is the supply plus the return side of the equation added together. You need to have both pieces to figure things out.
The main concern when we're talking about static pressure, if you're having problems, you talk to tech support, we don't care about all the other stuff that's around it. The filter, the evaporator coil, that affects it, yes. But when we're talking about that static, just remember that it's that immediate piece of equipment we're talking about, like the furnace. We don't care the extenuating stuff, all the stuff hanging on the outside that we figure out is maybe what's helping the static be bad or poor, however we want to look at it. But the main thing is when, tech support asks you for static pressure, we're looking for that static pressure of the furnace. The other stuff, why it's what it is, that's another story. And then you do your deducts and your math on that as we figure out for our air cleaners or our evap coils or whatever it is.
So in that regard, where do you want them measuring it for that part of the discussion?
To find out with the evap, the coil, we'd be measuring from above the bottom end of the evaporator coil to above the evaporator coil. So we'd be on both sides of the evap, just like for a filter, we'd be on both sides of the filter. And you could also look those up too, by the way. You could actually look up, if you look up on an evaporator coil and product data on evaporator coils, I believe that's where it's at. They will tell you what the static pressure is on that coil, and they'll tell you dry and wet. Because it's slightly different. Obviously, they can't tell you what that static pressure would be if that coil is dirty, because that varies. But they do have the static pressures listed for the evaporator coils and most air filters, or I should say air cleaners, whether it be a Honeywell or an Aprilaire or a Carrier electronic, whatever it might be. You can also look up those numbers too. So that stuff is available, but then you could actually physically do it with your manometer.
This is a CNPV coil, and the furnace we're looking at before was 60,000 3-ton drive. So let's assume 3 tons. This very bottom coil on the chart over here, if we gave it a traditional 1200 CFM desired airflow for 3 tons, this particular coil down at the bottom of the screen, if you looked at it, I just scrolled it up too high, is 0.259. So let's call it 0.26 dry and 0.31 wet. So to Dave's point, as you put your probe from this dot right here to this dot right here across the coil, that would be what you should see when it's clean, or when it's clean and dry, or when it's clean and wet. So that's a pretty good amount. Like this particular coil that we picked is probably pretty high, but 0.256, we'll just call it 0.3 for discussion standpoint. If the furnace is prepared to do 0.5 and you got 0.3 that's getting dedicated to the coil, that leaves 0.2 for everybody else. If we look at a particular filter, in this case, I took an Easy Flex. Scroll down here, the pressure drops, zoom it up a little bit. Let's say you have a MERV 10, which is what a lot of you guys use. And let's say, once again, it's a 3-ton example to keep everything consistent. So 1200 CFM, it's 0.13 pressure drop if you use the size 16 filter. And then it's less pressure drop, 0.09, if you use the bigger filter, the size 20. Obviously, bigger filter, more surface area, wider duct, so less pressure. Small restrictive ductwork contributes to your pressure problem. Larger, less restrictive ductwork and or filters helps your static pressure problem. Let's say, for sake of argument, that's 0.1, and you got 0.3 off the coil. That's 0.4 of a furnace that's prepared to deliver 0.5 to you. So if we take that a little further and put all that together, you zoom back where I can read. This table here, and this is for all furnaces, this is not just this furnace. Every furnace from every manufacturer has this kind of data. If we stay consistent to what we had, which is this 60,000 BTU, 17-inch wide, 3.5 ton drive cabinet, rated external static pressure. That doesn't mean it's the only static pressure it can operate at, but that's where they tested at. For heating mode is 0.12, and for cooling mode 0.5, because for cooling mode, you're probably gonna have a higher CFM, and you're also gonna have an evaporator coil, obviously. So you got 0.5 to work with on cooling, minus your coil, minus your filter. That doesn't leave a lot of room for ductwork. So if you have ductwork that's restrictive, it gets to be a problem really quick. Or you can just not put filters in your system. Seems like a simple.
You always have options. Life's about options.
In these same furnace books, if we scroll down to, where's the one we had? 60,000 BTU, 17-inch wide, 3.5 ton drive. You can get more detailed information for what happens if, well, what if my pressure is not exactly 0.5, right? External? What if it's something else, right? So if you have 0.7, for example, depending on which airflow speed you set it up for over here with the switches, or it could be an app, or it could be speed taps on an older furnace, but whatever speed you picked will make a difference. So if we had the 0.5 example, we happen to be at 0.5 for our duct static, and we happen to be at a cooling default speed, which is this top one right here, this guy would be producing 1190 CFM. And as the static increases, you can see what happens to the CFM that it can produce. If I got 0.8, I'm down over 100 CFM. If I got a full inch, I'm down 200 CFM. And as you get further to the right, the gap for each 1/10 of an inch gets bigger and bigger and bigger. If you ask it to run at a different speed, then it could be a different scenario, right? So the maximum, 1,475 CFM. If you're operating at 0.7, you're down to 1,340. If you're operating at 1 inch, you're down to 1,100. So you've lost 400 CFM by going from 0.5 to 1 inch external static pressure. It's a pretty big penalty. The higher static pressure resistance gets. So that's coil choices, that's filter choices, that's ductwork choices. See if anybody's got any questions for us. So nobody's typed anything in.
This explanation is too good.
Yeah, we're great. If you guys have some questions, we'd love to hear them, whether it's on this exact topic or something tangent to this. It's a big word. I don't know if I can use that word.
That's a French word.
Anybody have any questions we can address?
Just side note, guys, on again, the furnaces have quite a bit of tolerance built into them. So sometimes that's a complaint that comes up that, there's not enough tolerance on the equipment. There is enough tolerance. It's just when your static is out of hand, you can't blame the furnace for that. And again, a lot of that static issues and stuff comes from sizing also. Bigger is not better. It's said constantly, but yet still not always followed by a lot of people in our business. Just because you have a bigger blower doesn't mean you're gonna move more air necessarily. It's you gotta be able to move that air through the ductwork.
Yeah, and then you may be surprised to hear this, but the higher you run the fan, the more static you're gonna have. It's just like driving your car. Like if the road is smooth, there's not very much resistance to your car. You go drive down a gravel road with your engine at the exact same RPM, your car's not going to be able to accelerate as quickly because the gravel road gives more resistance. So the worse off and more restrictive your duct system is for a given fan speed, the worse off your static situation is going to be. And if you just keep ramping up the speed, you're going to keep increasing the static. These tables are just like a snapshot in time. So if you ramp it up, you're going to have more and more problem.
And noise/sound.
For sure.
Noise and sound doesn't mean good airflow.
Dave mentioned sizing, and you guys probably know me well enough to know that I like to complain about everything being oversized. And we have a debate all the time whether when there's problems with high static or high limits on furnaces or something like that, we always debate on whether the ductwork is too small, and usually it is, right? But it's too small for that furnace. And I usually end up arguing the ductwork is probably the right size. The furnace is too big. If you put a smaller furnace in, some of your static problems go away. Not all of them, but some of them do. It can help out with some of those problem airflow jobs. It doesn't mean you're going to get more air delivered to that crappy ass run to the bedroom above the garage. You're not going to solve that problem, but you might solve your high limit problems if you just stop putting in 120,000 BTU furnaces and only put in 60s and 80s.
40 sometimes too.
I think of whose house it was. I did a load calc for somebody's house at the office here last week, and it was like 40 some thousand BTUs for like 3,000 something square feet, and they just couldn't comprehend that was actually possibly accurate.
But you still got 100,000.
They had 200,000 at that house currently. I'll tell you whose house it is later. While we're waiting for you guys to type up some questions, there are a few other things we could point out to you. Earlier today in the lab here, I took a picture of one of the tags on a furnace in the lab. And there is some of this, obviously in a limited fashion, information on the furnace. I know it's hard to see the tags too, right, when I zoom up even. But one of the things that's on there, you'll see we maximum heating external static pressure in inches of water column, and that's 0.5. So that's what they're expecting you, even though the catalog shows data at 0.6, 7, 8, 9, and 1 inch, they're not expecting you to operate it there. They're expecting you to operate it at 0.5 or less when you're in the heating mode, right? When you're in cooling and you add an evaporator cooler to the system, that changes it up a little bit. But over here, they're testing your furnace here at 0.1, 0.2, somewhere in between there, depending on the size we showed you on the other one. And they're expecting you to keep it below the 0.5. So that's actually printed on the tag of every unit. I think almost every manufacturer uses the exact same 0.5. It'd be rare to see something that's not 0.5 for a residential furnace. Doesn't mean you can't operate at 0.6. It just means as you get further past 0.5, bad things happen. I don't know about Dave's impressions, but I feel like 0.8 is like the average around here. Most places I go to.
Yeah, 0.7 and 0.8 seem to be. And then once they don't even chart it, if you look in the books after 1, they don't even chart it. Because then you're so far out of the realm you should be. That you should correct the issue or try another line of work. But correcting the issue doesn't always work because there's an end user involved. So that's sometimes a game you have to play.
Yeah.
And they wait to hear what they want to hear from a dealer who's going to tell them, no, this is good, I'll do that, or no, you're right. And So like I said, that's stuff you guys in the field have to juggle with, which is difficult at times.
Yeah, the higher the static, the lower the CFM, as you can see on the chart. That's true for pretty much almost all types of systems. And then the symptoms of that are going to be hot spots on your heat exchanger, premature cracking of the heat exchanger, high limit trips on there. And then obviously on the refrigeration side, if you have too little bit of airflow and you have pressure sensors on the system, you can be tripping out as well.
And as far as taking your static, it's important to have a quality manometer from TEC, your local TEC stores. You should always buy one from TEC because I think they work better, maybe.
Is that just an empty bag?
No, we can pull it out. We could unveil
Dave
it.
just carries field piece bags around, and then he's got other brands of tools in there. So like a DG 100.
It's I don't know, because I don't have any glasses.
I have the same one. I don't have a cool bag though.
Yeah, you gotta have it's nothing's good if it doesn't have a good sack around it, whatever that means.
That's a dual port manometer, which is nice because then you can measure that supply static and the return side static at the same time. You do have to do the math to add them together. I know that's unpleasant for people. Math is not your friend usually.
But you have a cell phone.
All right, we do have a question from Brian, and he prefaces it with join the call late, which is what people always say when they are about to ask something we already covered. How much does the higher MERV ratings affect the system, specifically MERV 8? I don't have a MERV 8 example in front of us right now, Brian, but I do have an example we can look at the moment because it happens to be on the screen. On this here, they have a size 16 MERV 10 and a size 16 MERV 13. And on our example, which was 1200 CFM 3-ton system, 0.13 clean filter compared to 0.17 clean filter. So 0.04 in this particular example. If we went up to a larger airflow, 1600 CFM, 0.6 is my difference. And then if you go larger than that, you see the dashed line. You're not supposed to be using that filter on that particular airflow range. So there is a difference in MERV rating. The lower the MERV rating, usually the lower the pressure drop. This is not always true, though. It depends on how the filter manufacturer is getting the MERV rating. If they're getting the MERV rating higher by putting more dense media in there, it's going to be more restrictive, and hence there'll be a higher static pressure differential across the filter. But if they're getting a higher MERV rating by using technology, i.e. electrostatic contraction, then they can get a higher MERV rating and not have an additional extra pressure penalty. So if you have stuff like an Infinity air purifier, Secure Air, Ultra Clean 99, Respicare, Micro Clean 95, those types of things, a Honeywell electronic air cleaner, those types of things can have a decent MERV rating without necessarily having a high pressure drop associated with them. The other thing that can be done on filters to have a decent MERV rating without a high pressure drop is to make them deeper and hence have more surface area in the pleats. So if you have a MERV, in this example, we got MERV 13 at 0.17 pressure drop, but you could also have a MERV 13 in a 1-inch filter, which is much skinnier than this, and it might have a 0.3-inch pressure drop. I don't want to call any brands out by name, but there's a specific brand that you can pick up at Home Depot that has all these like high pollen filters, but they're all 1-inch because people buying things at Home Depot, they literally walk in there with the filter in their hand and they go on the shelf and find the one that matches the one that came out of their basement. And they need one that says 20 by 25 by 1. And that's the one they're going to buy no matter what anything else says. A 1-inch high MERV filter is usually a problem.
Cardboard is a great filter, but it doesn't let any air through. That's kind of.
What if I punch holes in it?
You get punch holes in it, then you get some air.
Nice. Also no filtering. In a pinch, you could just use a t-shirt.
It's good to have a question. Thanks for the question, Brian. I don't even know that I like anybody named Brian, so. But that's a tough call if we should have answered that for you or not. Nothing personal.
The same thing will happen with coils, right? If we have a coil that's a certain capacity of cooling and we're doing it in a little short stout cabinet versus one that's tall and has more surface area associated with it, you're typically going to have a higher static pressure drop through that as well. So sometimes the coils get, like, even though we've used end coils for a long time, they're nice because they fit in small spots. but sometimes fitting in a small spot means everything's jammed in there, which means it's a little more resistive.
With the static pressure, the main thing we hear about static pressure wise and why you're questioned or people are questioned, not necessarily you, when they call with limit issues specifically, furnace related. We'll ask what static pressure is because everything is good. Everything is perfect, but there's a reason your limit's going off. And so you have to pay attention, and static is a good indicator. It's easy to check. It's a good indicator of what's going on in the system. You could track your CFM with it because everything is charted. So once you know your static, you know what the CFM you're getting, and then you can look at the CFM you actually need for that unit. And again, things that are dirty affect that, whether it be dirty filters. We always, your evaporator coil, if that's dirty, that's going to obviously affect your airflow, affect your static. And along with that, if you have a real dirty filter and a dirty blower, but yet your evaporator is clean, you have a secondary heat exchanger on a 90% furnace, which also gets plugged up. So there's a number of things that cause static issues, limit issues, and this is a problem every year for tech support calls. Limits are constant calls, and usually no one could answer a question, what the gas pressure is, what the static is, what your temperature rise. So we try to kind of get across to everybody, taking static is real easy and it tells you a lot right out of the gate, so hopefully we can get more people to actually do it, especially as our technology improves and stuff with the equipment.
So the recommendation, if you're having these airflow issues and limit trips that you think is related to something in the equipment or mechanical room, do this supply and return to figure out your total external static. And then if it's higher than you expect, i.e. higher than the charts of that furnace show, or towards the high end of the charts, then like Dave said, you want to figure out which widget is causing the problem. So you're going to do what he said, take that manometer they just showed you and measure the pressure from here to here to see the coil, measure it from here to here to see the filter, measure it from where my mouse is to one of the far end inlets of the return duct to see what the pressure drop of the return section is. And you can find where that restriction is going to be. You can measure those things, compare them to what it says in these charts, whatever brand of things you have, and one of them is going to be way off. And you're like, oh, crap, that's not supposed to be that. And you're going to find out you do have a dirty coil, or you're going to find out that someone did swap that filter with a different kind of filter that you didn't know they swapped it out with or whatever. One of the other things that we wanted to show you, Dave shows this to a lot of people and sends it to them. I'm not going to play it for you. I'm just going to point this out. Our friend Corbett at Home Performance has a really nice short video. Anything under 15 minutes is something we can digest over here. He's a nice short video that just explains pretty much everything we just explained, but he's cooler than us. So you might listen to him instead of us. And he's also not an HVAC guy. He's a performance tester. He just tests stuff for people's houses, all kinds of different things, one of which happens to be static pressure. So this video is a nice one. I'm going to see if I can put this in the chat so you have the link to it if you want to watch it later. We can find where that goes in the chat. Do that. All right, you should have that link in the webinar chat, so that way you can click on that and watch it later. Does anybody have any other questions that you'd like us to answer related to static and airflow or other topics of interest? Sports, weather, our haircuts. We do get a lot of comments. We don't read all the comments that come in, but we get a lot of comments on how cool our haircuts are. It's a really big thing.
And if you have any sport comments or questions, just to be clear, the Cubs are not included in that.
We probably shouldn't include the White Sox right now either.
It's not a sport team.
We should ignore all baseball in Chicago right now. Probably not a good call. Let's just skip the politics and religion where it's safe. All right, we'll leave it on for like another 30 seconds or so in case someone else wants to type another question in. Otherwise, we're probably almost wrapped up here.
Again, if you guys have questions, don't hesitate to call tech support 708-418-7900. And Or if you have any ideas, stuff you want talked about, training, please let us know.
All right, looks like there are no other questions, so we're gonna go ahead and wrap it up. And let us know what topic you want to see next month. Thank you.
Hey, thanks, guys.